Welcome to the wonderful world of programming, where nothing ever made sense. Presented by Team Kyushley. Team Kyushley consists of Ashley Hunt, soon to be Hilton, and Kyujin Lee, still Lee. Our project was on cell towers for all. Our project problem statement was to create a map atlas for optimal cell tower placement for 4 different counties in Utah. The 4 counties that we chose were Salt Lake County, Weber County, Davis County, and Utah County. To find the optimal cell tower placement, we set 4 different parameters, which include distance from roads, distance from existing cell towers, slope, and distance from populated areas. Distance from existing cell towers so that time and money wouldn't be wasted on placing new cell towers near existing cell towers. Slope to find suitable locations to build cell towers. And distance from populated areas so that cell towers are placed in optimal locations near areas that are near cell towers the most. In order to begin the code, we first needed to collect the 4 DMs for each counties from gis.utah.gov. Then we collected all the necessary shapefiles, data for a county, existing cell towers, roads, and census data. Our solution was to create a Python code that creates a PDF map atlas file for each of the 4 counties in Utah, given the set parameters. For our project, we held distance from main roads, distance from existing cell towers, and slope as constant parameters, and set the distance from populated areas as our variable. This allows the end user to enter whatever value they choose to buffer around populated areas for each county.
Before writing the code, you will want to make sure that your ArcMap document is set up properly. You want to start out by organizing the file path for all the data collected earlier into separate files for DM, inputs, and scripts. It will be useful to organize your DM files like such. If you go into Data, here is the DM file, and see how we organized it with each individual county. As you can see right here, we have the folders for each individual counties with their required data sets. And here you can see the folder for the Python script if we go back. Right over here. So now if we go into ArcMap, you can see that all the required data are preloaded as such. And if you were to start out a new ArcMap, you'll want to import all the necessary shapefiles into ArcMap and organize them in the right data frame. After which, you'll want to set up the layout view so it's organized the way you would like it to appear in the final PDF map atlas file after the Python script runs each function. Here you can see that we have it laid out as such with the final suitable sites legend here and the buffer value input up here. So now when we go over here and open up the Python script, we can see that there is a line where the end user can see the select file path name. Under that, you can see that there are 4 different values you can enter for the buffer around populated areas right here. For this case, we've set default values to automatically fill in these buffer inputs in case the user either forgets or does not know what values to enter. Here we have the default values to be 100, 200, 500, and 1000 meters as the buffer. Next, you will see that there are 2 lines below, one asking for the geodatabase path name, and next the other one asking for the user to select the coordinate system. And I'll just go ahead and right there, you see the NAD 1983 UTM Zone 12N. Click OK. Then once that's finished, you click OK and you will see the code begin to run. While that code runs, we can go over and look at the Python script right over here. We go all the way up. For this code, we'll just go over each block section by section. And starting off here, as you can see the code, we first imported all the modules so that the code will run properly. And then next we checked all licensing that was required to properly run the code. Then we created a file path name where all of our data was going to be stored. Then we created a dictionary right here that contained all the county info with a subfolder, name, DEM file, and shapefile for each county as such. And then below that we have our environmental settings set up. And then we set up the Scratch workspace and created the working document variable as MXD and CDF. Next we set some parameters and projections. Here the parameters are named pop buffer 1, 2, 3, and 4. And then we set up a workspace for the geodatabase so that if the code needed to pull in either a shapefile or a layer, it would automatically do so without us manually specifying the file type. And then we made a list of the different buffer distances that we could refer back to later in our code. And then next we set up our PDF path, which is where our final PDF file would be saved right here. And then after that we checked to see if a PDF file already exists, and if it did exist, the code would automatically delete it. Then we wrote if-then statements to check if our folders had any output files from previous runs, but if it doesn't exist, then it would run past that line of code and continue on. And the next one is a loop. It pretty much repeats the if-then statement. We also included the delete folder function that deletes files in the Scratch space and then creates the PDF path. We then enter our main loop with 2 loops inside. This loop cycles through every county, and then the inner loop cycles through the buffer distance, which then jumps out of that loop and re-enters the main loop, cycling through the next county, and so on and so forth. In the inner loop, we see that we started by listing the variables of our inputs and output files. Because of the way our code is set up, it will temporarily save each variable in the database. And then once the variables are defined, we then see here how the calculations are performed right here. Here we calculated the slope in each DEM file and isolated the ones that were less than 5 degrees and buffered all the roads. These are the different buffer values you inputted in the script window box before running the code. And then next we ran the extract by mask tool, which essentially intersects the suitable slope with the buffered roads. We then did a clip tool to intersect the cell towers with the buffered counties. And then we ran a kernel density to calculate existing cell tower locations. Then we got the areas less than a certain density, just as you can see right there. Then we did a raster calculator and intersected with the tower density, as you can see right there, and the suitable slope to get our final site locations. After which we were able to output everything to the map, as you can see. Then, as you can see in this section is for updating the map elements, such as text and symbology. And then it's exported into a PDF save. And then finally, the final step was to delete output variables before the loop starts again.
Now that the code is finished running, we see that it took a total of 25 minutes and 13 seconds. If we go into our master file, we see that the final map atlas was created and saved. Here's the PDF file. And if we open that up, we see the final atlas that our code created. And because of some of the default values that we used for our buffer distances, it didn't greatly affect the results because they were so small. If you used larger values here, it would have made the maps look more different. So here is Utah County buffered at 100 meters, and you can see the not suitable areas versus the suitable areas in purple. And then here's Utah County buffered at 20, or 200, 500, and 1,000 meters. And then here we have Davis County, which at 100 meters, the suitable area is in green, and the black is not suitable. And again, here's Davis County buffered at 200 meters, 500, and 1,000 meters. Next we did Weber County, and here's it buffered with 100 meters, 200, 500, and 1,000. And then finally there's Salt Lake County. And because Salt Lake County already has high density of cell towers, there were no areas that were suitable for new cell tower placement, so all of this is not suitable at every buffer distance. And thank you for watching our presentation.